Hello, today we will be presenting you our medical imaging term project. We have worked on building a comprehensive X-ray simulator with extended source and 3D objects. Projection radiography is a fast imaging technique, and it relies on the transmission of X-ray beams through the anatomical structure of humans. Different tissues and organs inside the human body attenuate the ionizing radiation in different proportions. Hence, the attenuation coefficients differ between different tissues. And that's why the X-ray imaging technique provides good contrast in bones and objects. And previously in class, we have covered point sources and 3D objects and extended sources and planar objects. Through this project, we want to extend the previously covered concepts and include obliquities and detector blur within our project. Also, we will be simulating extended sources with 3D objects. We will be using monoenergetic sources through this project. We will be using extended X-ray sources. The first equation is the imaging equation for an X-ray source. The TZ element is for the transmittivity, and M is the depth-dependent magnification. H is the impulse response of the detector blur. We have treated the 3D object as a combination of many planar objects. We have taken slices of the 3D object and projected it onto the detector plane. And we have modeled the extended source as multiple point sources shifted through the space, and we have superposed superposed these sources. And for each point source, we have imaged the object, added the effect of point sources to simulate the effect of an extended source. We have used two data sets. The first one is the Zubal phantom. The Zubal phantom is a voxel-based human male phantom, which has a volume given by 243 by 128 by 128. The voxels are cubic and each have dimensions of 0.4 centimeters in X, Y, and Z directions. And we have used SimSet package to obtain the tables. In the SimSet package, we had the attenuation density and the density tables to calculate the attenuation. Our second data set was the 3D Shep-Logan phantom. It is a commonly used phantom in imaging, and we have used the phantom 3D function. The voxels are of size 128 by 128 by 128, and the cubic voxels are again with dimension of 0.4 centimeters in X, Y, and Z directions.
So the simulation setup and parameters used. For Zubal simulations, we will take the detector size as 150 to 70 centimeters. This is because we're doing a general projection radiography, and these are suitable size for the detector. For Shep-Logan simulations, we will take the detector size as 100 by 100 centimeters. This is a brain phantom, head phantom. Therefore, these sizes are suitable. We'll first place the imaged object on the detector, and then we'll bring the object closer to the source to see the effect of the distance between the source and the object on the projections. We're also going to look at the X-ray beam energy effect on the projections and the orientation of the objects as posterior to anterior and anterior to posterior. We'll also look at the effect of detector blur on the projections. And the parameters that we used are detector source distance, 185 centimeters, thickness of human, 28.8 centimeters, as measured from Zubal phantom, and 1.2 millimeter radius for the extended source. So our results, these are the results for investigating the effect of the distance between source and object on the projections. From left to right, we see it for 0 centimeters between the detector and the object, 15 centimeters between the detector and the object, and 30 centimeters. We see that the edge blurring effect increases as the gap increases, and the image becomes magnified. These are the same experiments done for the Shep-Logan phantom. We again see that the image is magnified and that there is edge blurring. For the energy, we have done this for 50 kilo electron volts, 100 kilo electron volts, and 200 kilo electron volts. These choices were done because diagnostic X-rays are generally less than or equal to 124 kilo electron volts. So we want to see the effect of the X-ray energy on the projections. We see that as the energy becomes 200 kilo electron volts, the contrast becomes much reduced and worsens. Also, we looked at posterior to anterior and anterior to posterior. The left image is posterior to anterior. In this image, we see the jaw and the face of the person more clearly, and also the rib cage. This is expected because the person is closer to the detector. The face and the rib cage is closer to the detector. And we see the opposite in anterior to posterior.
So finally, we have simulated the detector blur. We had a common typical modular transfer function in our textbook, and we tried to model it using a simple equation as shown here. And we had the parameter k to arrange the low pass frequencies of the filter. And we chose 3 values such that the blur was gradually increasing. So on the leftmost picture, we have the least blur. So the picture is clearer, and then to the right, the blur increases. On the rightmost picture, we see that the X-ray image is a lot more blurred than compared to the others. And the same values are used for the Shep-Logan phantom as well. And again, we see that the different structures inside the head becomes harder to distinguish as blur increases. So now I'll show you the code we wrote. So the code takes inputs as shown here. We first declare the energy of the X-ray, and then the orientation of the phantom, anterior to posterior or posterior to anterior. Then we define the distance between the detector and the phantom, and we define the radius of the extended source in centimeters. And then we choose the phantom, which phantom to use. 1 is for Zubal and 2 is for Shep-Logan. And then finally, we choose if we are going to do post-processing or not. And this post-processing process is just taking care of the obliquities by dividing the values by cosine cubed. Now, I previously did a simulation because it takes a long time. I've prepared the figures, and these are the parameters. And this one is the figure with k equals 20, so the least amount of blurring. And then I applied the greatest amount of blurring, which shows here blurred image. And to simulate the extended source, we have, again, as my friend said, acted like it was a combination of point sources. And here we see that for each of these point sources, we simulate an imaging process, and then we add all of those effects to simulate an extended source. So thank you for listening. That's all.